Welcome to Earthly Teachings, where learning is clear and powerful. Today we are working on Mathematics N6. Let's learn together. In this video, we'll dive deep into solving second-order linear differential equations. We'll tackle two main types of problems. First, we'll learn how to find the general solution for a variety of these equations. Then, we'll take that general solution and find a specific or particular solution using given initial conditions. By the end of this tutorial, you will be able to confidently identify the type of solution needed, apply the correct formulas, and work step by step through any second-order linear differential equation you encounter in your N6 studies. Let's get started. Let's begin by introducing some key definitions and the general approach for solving these equations. This will provide a solid foundation for the problems that follow. Our focus today is on the general form of a second-order linear differential equation. Here y is the dependent variable, x is the independent variable, and a, t, b, and c are coefficients that can depend on x. For our N6 curriculum, we are primarily interested in a simpler but very powerful version. We will be solving equations where the coefficients are constants, which we'll call a, b, and c. The right-hand side, fx, determines what type of solution we'll be looking for. If fx is 0, the equation is called homogeneous. If fx is not 0, the equation is called non-homogeneous. Solving these equations might seem intimidating at first, but there's a systematic approach. For non-homogeneous equations, the general solution, yg, is the sum of two parts. The general solution, yg, is the sum of the complementary solution, yc, and the particular solution, yp. The complementary solution, yc, is what you get when you solve the homogeneous version of the equation, meaning you set the right side, fx, to 0. This is a crucial first step for every problem. The particular solution, yp, is any specific solution that makes the non-homogeneous equation true. We find this part by making a guess based on the form of fx and solving for its coefficients. You'll see this method applied repeatedly in the coming examples. Remember this fundamental structure. First find y at gui, then find y kapai. Add them together to get wi chikar. This is the cornerstone of our entire process. Let's focus on that all-important first step, finding the complementary solution, wakapo. This involves solving a homogeneous equation. The general form of a homogeneous equation is a times the second derivative of y plus b times the first derivative plus c times y equals 0. The key is the equals 0 on the right side. To solve this, we make a clever guess for the solution. Y is e to the power of mx, where m is a constant we need to find. Let's see why this works. If e is e to the power of mx, then its first derivative is m times e to the power of mx, and its second derivative is m, squared times e to the power of mx. We get a simple power of m. Substituting these back into the homogeneous equation, we can factor out e to the power of mx. The only way this entire expression can be 0 is if the part in the brackets is 0, since e to the mx is never 0. This gives us what's called the auxiliary equation, or characteristic equation. It's a simple quadratic equation. The roots of this equation will give us the values for m, and those values will determine the form of our complementary solution. There are three possible types of roots for this quadratic equation. Let's look at each case. Case 1. The roots are real and distinct. This is a very common scenario. This happens when the discriminant of our quadratic formula, which is b squared minus 4ac, is greater than 0. We will get two different real numbers for m. Let's call them m1 and m2. When the auxiliary equation has two distinct real roots, m1 and m2, the complementary solution is a simple combination of two exponential functions. The formula for yc is c1 times e to the power of m1x plus c2 times e to the power of m2x. Here, c1 and c2 are arbitrary constants. Let's work through an example to see this in action. Consider problem 1.1. d2 plus y x2, 3dy dp equals 0. First, we write down the auxiliary equation. We replace the derivatives with powers of m. The second derivative becomes m squared, the first derivative becomes m, and y becomes 1. So we have m2, 3 minus 4 equals 0. Next, we solve this quadratic equation. This one can be factored. We need two numbers that multiply to -4 and add to -3. Those numbers are +1 and -4, so the factors are m plus 1 m 4 equals 0. Setting each factor to 0 gives us our roots. m1 equals 1 and m2 equals 4. These are two distinct real roots. Now we can write down our general solution, which in this case is the complementary solution since the equation is homogeneous. Using our formula, the general solution is c1 times e to the power of -x plus c2 times e to the power of 4x. And that's our complete answer for this problem. So, to recap, for real and distinct roots, form the auxiliary equation, find the roots using the quadratic formula or factoring, and plug them into the YC formula. This is the simplest case, and a great one to practice first. Now let's move on to the second case. The roots are real and repeated. This occurs when the discriminant, b squared minus 4ac, is exactly equal to 0. In this situation, the quadratic formula will only give us one distinct real root, but we count it as having a multiplicity of 2. Let's call this repeated root m. When the auxiliary equation has a repeated real root m, the complementary solution takes on a slightly different form. The formula is YC equals c1 times e to the power of mx plus c2 times x times e to the power of mx. Notice that second term is the first term multiplied by x. This is what makes the two parts of the solution linearly independent, which is a key requirement for the general solution. Let's demonstrate this with an example. Consider problem 1.3. T put dx2 plus 8 dy dx plus 16 equals 0. As always, our first step is the auxiliary equation. Replacing the derivatives, we get m2 plus 8m plus 16 equals 0. This quadratic equation is a perfect square. It factors nicely into m plus 4 2 is 0. Setting this to 0 gives us our root. We find a single root, m on actual 4. Because of the exponent of 2, we know this root is repeated. Now we can construct the general solution using the formula for repeated roots. Plugging our value of m equals 4 into the formula, the general solution is c1 times e to the power of 4x plus c2 times x times e to the power of 4i. And that's our final answer. A common mistake here is to forget the x in the second term. Without it, you only have one linearly independent solution, not two, and the general solution won't be correct. Always remember that x for repeated roots. We've covered real and distinct roots, and real and repeated roots. Now for our third and final case, complex roots. This happens when the discriminant b squared minus 4ac is less than 0. When you try to solve for m using the quadratic formula, you'll end up with the square root of a negative number. The roots will always appear in conjugate pairs. This means if one root is alpha plus I beta, the other must be alpha minus I beta, where I is the imaginary unit, the square root of -1. Here, alpha is the real part and beta is the imaginary part. Using Euler's formula, which connects complex exponentials to trigonometric functions, we can derive a solution in terms of sines and cosines. This is much more practical for most applications. The complementary solution for complex conjugate roots is e to the power of alpha x times the quantity c1 cosine of beta x plus c2 sine of beta x. The real part of the root, alpha, goes in the exponent, and the imaginary part, beta, goes inside the sine and cosine functions. Let's apply this to an example. Consider problem 1.2. 2 dx2 2 dy dx plus 5ix 0. First, we set up the auxiliary equation. This gives us m2, 2m plus 5 equals 0. Let's check the discriminant. b2 4ac equals 2 2 4 1 5 is 4 and 20 equals 16. Since it's negative, we'll have complex roots. We must use the quadratic formula to find the roots. m equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Plugging in our values gives m equals 2 plus 16, 2. The square root of -16 is 4i, so m equals 2 plus 4i equals 2, which simplifies to m equals 1 plus 2i. Now we identify our alpha and beta. The real part, alpha, is 1 and the imaginary part, beta, is 2. Notice we use the positive value for beta. Finally, we can write the general solution. The general solution is y cosecant g equal e to the power of x times the quantity c1 cosine of 2x plus c2 sine of 2x. This represents an exponentially growing or decaying oscillation. To recap the cases for finding yc, for distinct real roots, use e to m1x and e to m2x. For repeated roots, use e to mx and x e to mx. For complex roots, use e to alpha x with sine and cosine of beta x. Knowing these three templates is essential. Now that we are masters of finding the complementary solution yc, let's turn our attention to the particular solution yp, which is needed for non-homogeneous equations. We use a method called undetermined coefficients. The idea is simple. The form of the particular solution yp will match the form of the right-hand side of our differential equation, fx. There are three main cases for fx. Case 1. If x is a polynomial, say, of degree n, then we guess a general polynomial of the same degree for y pt. For example, if fx is x squared, we guess yp x2 plus bx plus c. Case 2. If fx is an exponential e to the power of ke, our guess for yp is a times e to the power of ke. The coefficient a is what we need to find. Case 3. If fx involves sine or cosine with argument kx, our guess must include both. We guess y equal to a cos k plus b sin kx. This is because the derivative of cosine is negative sine, and the derivative of sine is cosine, so we always need both terms. Once we have our guess, we substitute it and its derivatives back into the original non-homogeneous differential equation. Then we collect terms and equate the coefficients on both sides to solve for our undetermined constants, a and b. This method requires careful differentiation and algebra, so it's a good place to double-check your work. Now let's practice this with a problem. Let's apply the method of undetermined coefficients to solve a full non-homogeneous problem. Consider problem 1.10. d² by x2. 2d dx plus 5e equals 8e to the power of x. This equation has a right-hand side, so it's non-homogeneous. Our general solution will be y yc plus y. Step 1. Find the complementary solution, you see. We solve the homogeneous version. 2y min x2, 2dy x plus 5 equals 0. The auxiliary equation is m2, 2m plus 5 equals 0. Notice this is the exact same equation we solved in the complex roots example. This is not a coincidence. We know from our previous work that the roots are mi equals 1 plus 2i. This means alpha is 1 and beta is 2. Therefore, our complementary solution is y sox e to the x times the quantity c1 cos 2x plus c2 sin 2x. Step 2. Find the particular solution, yp. The right-hand side, fei x, is 8e to the x. This is an exponential function. Our guess for yp must be the general form of an exponential. We will guess yp a times e to the x. Now we need to find the derivatives of our guess. Since the derivative of e to the x is just e to the x, both the first and second derivatives of our guess are also a times e to the x. Substitute these back into the original non-homogeneous equation. We have ai to the x minus 2 times ai to the x plus 5 times ai to the x. This must equal the right-hand side, 8e to the x. Combining the terms on the left gives us a 2a plus 5ae to the x equals 4ae to the x. This must equal 8e to the x. Equating coefficients, we can see that 4a must be equal to 8. Solving for a, we get a equal 2. Plugging this back into our guess, the particular solution is y bc on 2e to the x. Step 3. Combine yc and yp. The general solution is the sum of our two parts. So yg e to the x times cc1 y cos 2x plus c2 sin 2 plus 2e to the x. This is our final answer for the general solution. Always remember the three-step process for non-homogeneous equations. Yc, ycop, then add them together. This structured approach will guide you to the correct solution every time. There's a special condition to be aware of when choosing your guess for the particular solution, yp. It's called the case of duplication. The rule is simple. The form of your particular guess, YIP cannot be the same as any part of your complementary solution YC. If it is, you must multiply your guess by x. This might sound a bit abstract, so let's work through an example to make it clear. Consider problem 1.11. 2 dx2, 3dy x 4y equals 3e to the power of 4. Step 1. Find the complementary solution, you see. The auxiliary equation for the homogeneous part is m2, 3m 4 equals 0. This is the same equation from our first distinct real roots example. The roots are 1 equals 1 and m2 is 4. So our complementary solution is yc equals c1e to the power of x plus c2e to the power of 4x. Step 2. Find the particular solution, yip. Here's where the duplication comes in. The right-hand side, fi sat, is 3e to the power of 4x. So, our first instinct is to guess yp equal a times e to the power of 4x. Now, we check for duplication. Is any part of our guess in yc? Look at yc. We have a term c2e to the power of 4k. Our guess, aa to the power of 4x, has the exact same form. This is duplication. This guess won't work. What do? The rule says we must multiply our guess by x. Our corrected guess for the particular solution is y up e times x times e to the power of 4x. This is no longer a duplicate and will work. This is the most critical step for this type of problem. Get the guess wrong and the whole solution will be incorrect. Always compare yp with yc. Now let's proceed with finding a. This will require the product rule for differentiation. The first derivative, yp prime, is a times e to the 4x plus 4ax e to the 4x. The second derivative, yp double prime, is 4ae to the 4x plus, using the product rule again. 4ae to the 4x plus 16ax to the 4x, which simplifies to 8ae to the 4x plus 16x to the 4x. Substitute these back into the original non-homogeneous equation. This is a long substitution. Pay close attention to the signs. We have the second derivative, minus 3 times the first derivative, minus 4 times the original guess. Now let's expand and simplify. First we expand everything. Then we collect the terms with xe to the 4x and the terms with e to the 4x. Notice that all the terms with xe to the 4x cancel each other out. We're left with 5a times e to the 4x equals 3e to the 4x. This cancellation is a hallmark of the duplication case. The x in our guess made this happen. Equating the coefficients of e to the 4x, we get 5a equals 3, which means a equals 3 5. So our particular solution is yp mai popos 3 5c to the 4th. Step 3. Combine yc and yp. The general solution is yget c1e to the x plus c2e to the 4x plus 3 5xe to the 4x. Always remember to check for duplication. Let's work through another duplication case, this time with a repeated root in the homogeneous solution. Consider problem 1-8. Squared y over dx squared plus 8 dy over dx plus 16y equals 8. Step 1. Find yc. The auxiliary equation is m squared plus 8m plus 16 equals 0. We've seen this before. It's a perfect square, and m plus 4 squared equals 0, which gives us a repeated root m equals 4. The complementary solution is yec equals c1e to the sec 4x plus c22xe to the 4x. Don't forget that x. Step 2. Find yp. The right-hand side, fca, is a constant, fx, equals 8. A constant is a polynomial of degree 0. Our initial guess for a degree 0 polynomial is just a constant, let's call it a. So, our guess is ypqa. Now, we check for duplication. Is our guess a part of yat? No. The terms in yc are c1 times e to the 4x and c2 times xe to the 4x. Neither of these is a constant like a, so there is no duplication this time. Therefore, our initial guess is correct, and we can proceed. If yp equals a, its first derivative is 0 and its second derivative is also 0. Substitute these back into the original equation. We get 0 plus 8 times 0 plus 16 times a equals 8. This simplifies to 16a equal 8. Solving for a, we find a equal mahado. So our particular solution is the constant yp equals 1 5. Step 3. Combine yc and yp. The general solution is yg equals c1e to the 4x plus c2xe to the 4x plus 1/2. This completes the problem. This example shows that duplication is not guaranteed. Always check carefully before multiplying by x. Now let's tackle a more complex particular solution problem where the right-hand side is a polynomial. Consider problem 1.12, but with y and x instead of x and t to keep the notation consistent. So d2y dx2 plus 2 dy 6 equals 12 Step 1. Find yc. The auxiliary equation is m2 plus 2m plus 6 equals 0. Let's use the quadratic formula. E equals tar2 plus 20 cos 2. The square root of 20 is I times the square root of 20, which is 2I times the square root of 5. So m equals 1 times side. We have complex roots with alpha equals 1 and beta equals 5. The complementary solution is y assu e to the x times c1 cos 5 plus c2 sin of 5. Step 2. Find y bar p. This is the main focus here. The right-hand side, fx, is 12 by 2. This is a quadratic polynomial. Our guess for y of p must be a general polynomial of the same degree. Let's check for duplication first. Does a simple quadratic term like x2 appear in yc? No, the terms in y cross c are exponential and trigonometric, so there's no duplication. Our guess is valid. We guess yp equal x2 plus bx plus. Now we differentiate our guess. The first derivative, yp prime, is 2ax plus b. The second derivative, yp double prime, is just 2a. Substitute these into the non-homogeneous equation. We get 2a plus 2 times 2ax plus b plus 6 times x2 plus bx plus c equals 12x2. Now, the key is to expand and collect terms by power of x. This will allow us to equate the coefficients on both sides. First, we expand everything. Then we group the x squared terms, the x terms, and the constant terms. Now we compare the coefficients of the powers of x on both sides. For x squared, we have 6a on the left and 12 on the right, so 6a equals 12. For x, we have 4a plus 6b on the left and 0 on the right, so 4a plus 6b equals 0. For the constant term, we have 2a plus 2b plus 6c on the left and 0 on the right. We now have a system of 3 linear equations. We can solve them in order. From the x squared equation, we get a equals 2. Substituting this into the x equation, we get 4(2) plus 6b equals 0, which means 8 plus 6b equals 0, or b equals 8(6) equals 4(3). Finally, substituting a 2 and b 4(3) into the constant equation gives c equals 4(9). Now we have our coefficients. The particular solution is yp sub c 2 pi 2, 4(3x) plus 4(9). Step 3. Combine yc and yp. The general solution is the sum of our complementary and particular parts. It's a bit long, but we found it systematically. The key is the expansion and equating of coefficients. So far, we've found general solutions, which contain arbitrary constants c1 and c2. Often, we want to find a specific or particular solution that fits a set of initial conditions. A particular solution is found by taking the general solution and using given information about y and its derivatives at a specific point, often x is 0. These are called initial conditions. A typical set of conditions for a second-order equation would be the value of the function y and its derivative di dx, both at a single point x. The process is straightforward. First, find the general solution y chi dash, then use the first condition, y x0 x k1, to form an equation involving c1 and c2. Next, differentiate yg to get yg prime, and use the second condition, y x0 equal k2, to form a second equation. Solve the resulting system of two equations for c1 and c2, and substitute those values back into the general solution. Let's work through a full particular solution problem. This combines everything we've learned so far. Consider problem 2.1. 2d2y dx2 plus di yt 6y equals 7e to the power of 2x with the initial conditions y0 to 1 and y0 2. Step 1. Find the complementary solution, yc. The auxiliary equation is 2 plus m 6 equals 0. We can solve this quadratic by factoring or the quadratic formula. Let's factor. The factors are 2 master 3, m plus 2, equals 0. This gives us two distinct real roots, m to 1 equal 3 a 2 and m to 2 equal 2. Our complementary solution is y equal to c1e to the power of 3 2x plus c2 e to the power of 2x. Step 2. Find the particular solution, p. The right-hand side is fx equals 7e to the power of 2. Our initial guess would be yp as ae to the 2x. Let's check for duplication. Looking at yc, we see the term c2e to the power of 2x. Our guess is a duplicate. Therefore, we must multiply by x. Our corrected guess is yp is axe to the power of 2x. Now we differentiate using the product rule. The first derivative is ae to the 2x minus 2axe to the 2x. The second derivative is 4ae to the 2x plus 4axe to the 2x. Substitute these into the original non-homogeneous equation. We have 2 times the second derivative plus the first derivative minus 6 times the guess. This must equal 7e to the 2x. Expanding and collecting terms, we find that the xe to the 2x terms cancel, leaving us with 7a e to the 2x equals 7e to the 2x. Equating coefficients. 7a equals 7, so a equals 1. The particular solution is ypexe to the power of 2x. Step 3. Form the general solution y. Combining our parts gives y and c1e to the power of 3 to 2x plus c2e to the power of 2x minus xe to the power of 2x. Step 4. Use initial conditions to find c1 and c2. Our conditions are y01 and y02. First, we use y01. We substitute x0 into y and set it equal to 1. I0e, c1 e to the 0 plus c2 e to the 0 minus 0 times e to the 0. Remember that e to the 0 is 1, so we get 1 equals c1 plus c2. This is our first equation. Next, we need the derivative of y g. Let's be careful with the product rule on the last term. I part g prime is 3 to 2, c so y1 e to the 3 to 2ix minus 2c2 e to the 2x, and the derivative of the last term is e to the 2x minus 2x e to the 2x. Now we use the second condition, yata 0 2. Substitute x0 into yg prime and set it equal to 2. G prime at 0 is 3 to 2, c1 minus 2cr2 minus 1. This equals 2. Rearranging this gives our second equation, 3 2 c to 1. 2c2 equals 3. We now have a system of two linear equations with two unknowns, c1 and c2. Let's solve by substitution. From equation 1, c1 equals 1, c2. Substitute this into equation 2. This gives 3 to 2, 1, c2. 2c2 equals 3. Solving for c2, we find c2 equals 3 7. Plugging c2 back into c1 equals 1. c2 gives c1 equals 10 se. Step 5. Write the particular solution. We substitute our calculated values of c1 and c2 back into our general solution yg. The particular solution is 10 7e to the power of 3 and 2 minus 3 7e to the power of 2x minus xe to the power of 2x. This is the unique solution that satisfies both the differential equation and the initial conditions. This problem illustrates the entire process, from finding roots to solving a system of equations. Practice each step, and you'll be able to solve any particular solution problem. Let's work through another particular solution problem, this time with polynomial initial conditions, to consolidate our understanding. Consider problem 2.2. d2y was dx2 plus 4 dr dx plus 13 alex 26 16x 9 with the initial conditions y 0 1 and y 0 8. Step 1. Find yc. The auxiliary equation is m2 plus 4m plus 13 equals 0. The discriminant is b2. 4ac equals 16, 52 equals 36, so we have complex roots. Using the quadratic formula, m equals 4 plus 36, 2 equals 2 plus 3i. Alpha is 2, beta is 3. The complementary solution is yce to the 2x times cec1q as 3ex plus c2 sin 3x. Step 2, find yp. The right-hand side is a quadratic 26 by 2 plus 16 sides or 9. The guess is a general quadratic. I by p equals x2 plus bx plus c. There's no duplication with yc. The derivatives are yp else 2ax plus b and yp else 2a. Substitute into the equation. We get 2a plus 4 2ax plus b plus 13x2 plus b plus c equals the right-hand side. Expand and collect terms. Expanding gives 2a plus 8ax plus 4b plus 13ax2 plus 13bx plus 13c. Grouping by power of x gives 13ax2 plus 8a plus 13bx plus 2a plus 4b plus 13c. Equate the coefficients. For x2, 13a is 26, so a else 2. For x, 8a plus 13b equals 16. Substitute a out 2 to get b to 0. For the constant 2a plus 4b plus 13c is 9. Substitute ax2 b 0 to get c1. The particular solution is yp in 2 to 1. Step 3. Form the general solution y. Y equality to the 2x times cc1 cos 3x plus c2 sin 3x plus 2x2 1. Step 4. Use initial conditions I0 1 0 8 E0 1. Substitute x0 1 equals c1 1 plus c2 0 plus 0 1. This gives c1 equal 2. Now we need yh prime. Differentiate yg using the product rule on the first term. This gives yg prime. I0 8. Substitute x at 0. 8 equals to 2c to a 1 plus 3c key 2. We found c1 2. So 8 equals 4 plus 3c2, which gives c2 equals 4. Step 5. Write the particular solution. Plugging ck1 equals 2 and c2 equals 4 into the general solution gives y equal e to the chi x times 2 cos 3x plus 4 sin to 3x plus 2x to 1. Let's summarize the key strategies we've learned today, along with some final tips for exam success in Mathematics N6. First, for any second-order linear differential equation, remember this blueprint. General solution equals complementary solution plus particular solution. Second, always start with the complementary solution. Form the auxiliary equation am squared plus bm plus c equals 0. Solve it to find the roots, and then use the correct formula for y sub c based on whether the roots are distinct real, repeated, or complex conjugates. This is the foundation. Third, move to the particular solution for non-homogeneous equations. Use the method of undetermined coefficients. Your guess for y sub p depends directly on the form of f of x. Crucially, always check for duplication with your y sub c before you start differentiating. If there's a duplication, multiply your guess by x. Here are some common guesses. Finally, for particular solutions, don't forget to use the initial conditions. Set up a system of equations by plugging in the initial conditions into y sub g and y sub g prime. Solve for c1 and c2. This will give you the single specific solution you're looking for. A quick memory tip. The x in xe to the mx is there to fix duplication. It's like a penalty for a bad guess. Common traps to avoid: forgetting to check for duplication, making differentiation errors, and being careless with algebraic signs. Work slowly and check your steps. Exam strategy. Even if you get stuck on finding y sub p, find y sub c anyway. This often earns you partial credit, and you can still use it to form a system of equations with the initial conditions, even if the result isn't a final answer. And remember, you can always check your polynomial solutions by substituting them back into the original differential equation to ensure both sides match. That's a powerful way to confirm your answer. Thank you for watching. Like, subscribe, and continue learning with Earthly Teachings. We'll see you in the next video.